Namaste and welcome. Kasto cha? Have you ever stopped to think how all these devices around us, laptops, phones, even smartwatches, कसरी एकअर्कासँग कुरा गर्छन् instantly, चाहे एउटै कोठामा होस् वा संसारको अर्को कुनामा?
एकदमै फ्यासिनेटिङ प्रश्न हो।
आज हामी यही अदृश्य कनेक्सन, कम्प्युटर नेटवर्क्स र अझ खासमा तिनीहरू कसरी फिजिकली र लजिकली जोडिएका हुन्छन्, नेटवर्क टोपोलोजिज बारे अलि गहिरिएर कुरा गर्दैछौँ. We have some really good source materials to guide us.
Exactly. We'll be exploring the fundamental concepts of how devices are interconnected, primarily for resource sharing and communication. यो आजको digitally connected world को लागि एकदमै crucial topic हो.
Okay, let's dive right in then. Based on these sources, एकदमै basic levelमा, what exactly is a computer network?
Fundamentally, a computer network is simply a collection of autonomous computers or devices interconnected, kina, to share resources.
Resources bane. Hardware, software.
Both, actually. Hardware like printers, scanners, any data, files, information, any device sharing or receiving data. That's a node. They connect via channels. अब a channel guided huna sakcha, like cables, fiber optics, or unguided, like wireless signals, Wi-Fi, Bluetooth. The main goal, as the sources state, is information exchange and the biggest example, the Internet. A network of networks. Hainata?
Right, the ultimate network. So the sources talk a lot about the uses. Resource sharing ta bhayo. What are some other key benefits mentioned?
Well, beyond sharing printers and scanners, it's huge for file sharing, collaboration. Then there's communication, email, instant messaging, video calls, all network dependent. Ani, flexible access. This is interesting. The nodes say networks attempt to end the tyranny of geography.
And the tyranny of geography. Wow. That means working from anywhere, accessing information globally?
Precisely, it enables business operations across locations, home entertainment, remote education, telemedicine, in healthcare, even environmental monitoring. So, advantages like convenience, cost efficiency in the long run, and enhanced communication are clear.
Tara, surely it's not all positive. Faida matri ta pakkai chaina hola. What are the potential downsides the sources highlight?
Absolutely. There are trade-offs. Security is a big one. Networks, by definition, are points of access. So they are vulnerable to viruses, malware, hacking, data breaches.
That's a major concern, definitely.
Then there's the potential for lack of robustness. Depending on how it's built, a single failure, say a cable cut or a device malfunction, can bring down large parts of the network.
Ani, setup costs can be significant initially. Hardware, software, skilled personnel chahiela, maintenance na.
Makes sense. Risk management and performance depend heavily on the structure, hainata. This brings us to network topology. Yo shabd bar-bar aayi rahego cha. What exactly does topology mean in this context?
Topology refers to the network's layout or structure. Kasari nodes haru arranged chan and connected chan. There are two aspects. Physical topology.
The actual physical arrangement. Wires, devices.
The geometric layout, where the cables run, where devices sit. And then there's logical topology.
Logical? How data flows. Exactly. It's about how data actually travels between nodes, which might follow a different path than the physical wiring suggests. Understanding topology is critical because the choice heavily impacts performance speed, potential bottlenecks, plus cost, reliability, and scalability. Matlab network lai pachi expand garna kati sajilo cha.
This is where it gets really practical. Let's look at the specific topologies mentioned in the sources. How about the bus topology? Sounds like the simplest one.
It is, conceptually. You have one single main cable, the backbone. All devices connect to this backbone using drop lines and taps. It's cheap, relatively easy to implement for small networks. Uses less cable overall compared to others.
Sounds good, but what's the catch?
The catch is that backbone cable itself. It's a single point of failure. If that mean cable breaks anywhere, poof, the entire network segment is down. Adding or removing devices can also disrupt the network temporarily. Any troubleshooting kahan problem bhayo banera patta lagauna can be difficult. Signals also weaken as they travel along the backbone.
Okay, so that central vulnerability is a big issue. What about the star topology? This seems much more common now, especially in offices.
Very common, especially in LANs. Here, each device connects point-to-point directly to a central controller, usually a hub, switch, or router.
So everything radiates outwards from the center, like a star.
The big advantage is robustness. If one device's cable fails, only that device is affected. Aru network chali rahansa. Setup and modification are generally easier too. Fault identification is simpler. Problem chavane praya central device mane point karsa.
But isn't that central device itself a weakness?
That's the main disadvantage, yes. It's a single point of failure. If the central hub or switch fails, the entire segment connected to it goes down. It also tends to require more cabling than a bus topology.
Got it. Okay, next up, ring topology. How does that work?
In a ring, each device is connected to exactly two neighbors, forming a ring or circle. Data typically flows in one direction, passing through each intermediate device. Often, devices act as repeaters to regenerate the signal as it passes.
Advantages, disadvantages.
Locating cable failures can sometimes be easier than in a bus. Installation difficulty is moderate. Disadvantages include that expansion or modification can disrupt the entire network. And similar to the bus, a single break in the cable itself can bring the whole network down.
Token passing. Now, mesh topology. This one sounds like the most robust, maybe the most complex.
It certainly offers the highest reliability and robustness. In a full mesh, every single device has a dedicated point-to-point link to every other device.
Every device connected to every other device? That sounds like a lot of connections.
It is. The formula is n-1 2 links for n devices. So it gets complex and expensive very quickly due to the sheer amount of cabling and the number of ports required on each device. Installation is complicated.
But the advantage must be significant reliability.
Huge advantage. With so many redundant paths, if one link fails, data can easily be rerouted. It eliminates traffic problems on shared links because links are dedicated. It also offers enhanced security and privacy for those point-to-point links. However, because of the cost and complexity, full mesh is rare. Partial mesh, where only critical devices are interconnected in a mesh-like fashion, is more common. The Internet backbone uses mesh principles.
Okay, and the sources briefly mention tree and hybrid topologies?
Tree topology is essentially hierarchical. Think of it like an extended star topology. You might have a central backbone, like a bus, and multiple star networks branching off it. It's common in larger LANs, maybe a campus network with core, distribution, and access layers. It's scalable, but troubleshooting can be complex, and failure of a node higher up in the tree affects everything below it.
And hybrid. Hybrid is simply combining two or more different topologies. For instance, you might have a main ring backbone connecting several departmental star networks. The goal is to leverage the strengths of different topologies and minimize their weaknesses. Most large, real-world networks, like universities or even the Internet itself, are effectively hybrid. Wireless topologies were also mentioned, offering flexibility but with their own challenges like interference and security. So, wrapping this up, it seems pretty clear there's no single best topology. The choice really depends heavily on the specific needs of the network, balancing cost, reliability, performance, scalability, and how easy it is to manage.
Exactly right. It's all about trade-offs. Each structure, bus, star, ring, mesh, tree, hybrid, offers a unique set of pros and cons. You have to match the architecture to the requirements.
A fascinating look at the underlying structures that connect our digital world.
Indeed. And here's a final thought based on this material. Given the exponential growth in connected devices, the Internet of Things, and the sheer volume of data, how might these fundamental topology designs need to evolve or combine in even more intelligent, perhaps self-adapting or self-healing ways to meet the future challenges of networking at scale?
That's a really interesting question to ponder, something for our listeners to think about. Azakulagi ettinei. Thanks for joining this exploration of network structures. Peri betola.